Okay, all right. So let's get started. So, welcome to this talk. So, today I'm gonna report some of the recent results we have working on in the last couple of months. And the title is Impact of Underwater Glider Observation on Forecast of Hurricane Gonzalo. And this work is supported by the ML PhD Underwater Glider project. And first, I would like to thank our collaborators. Gustavo, Ricardo, Sanki, and Francis first, and all the others in the observation team for their great efforts on the observation part. And thanks for George and Michael doing the ocean data simulation work. And Hingsu of EMC provide the help with H-WRF HICOM coupling system. And this is a collaboration of all the people here. So the motivation why we are doing this work. So, as we know, the wind-induced SST cooling from the underlying ocean can affect tropical cyclone intensity, which makes coupled atmosphere ocean models necessary to obtain an accurate TC forecast. And as early as in 2004, Wan Wu to tropical cyclone experts has already recognized these. So quote from one of their review papers is that it's no doubt that future prediction of TC should include the coupling with the ocean. In that case, however, the initialization and data simulation of the ocean will become critical. Remember, this is 2004, but up to today, the study on how the ocean data simulation can impact the TC coupling forecast is still very limited. So that's one of the motivation we want to do this study. We want to investigate the impact of ocean data simulation on tropical cyclone forecast. So some words about the underwater glider, because this work is based on supported by this project. So LML have these underwater glider observations put them in the Caribbean Sea and tropical North Atlantic Ocean in support of studies, TC studies. The goal of this project is mainly to enhance our understanding of Earth's interaction processes during hurricane force wind events. And for the underwater glider observations, it can provide temperature and salinity profiles up to 1 kilometer depth. And the glider can be piloted along the predetermined tracks and be configured at any time to update the navigation and other relevant parameters, for example, the sampling frequency. So it provides a cost-effective alternative over the other targeted ocean observations, say XBT. And so in this study, we're going to evaluate the impact of assimilating the temperature and salinity data collected from the underwater gliders on tropical cyclone forecasts. And we are not only limited to the underwater glider, we're also trying to investigate the impact of different ocean platforms on the tropical cyclone intensity forecast. So the case study here we have is Hurricane Gonzalo of 2014. Well, at the time, is the strongest hurricane in North Atlantic since Igor. And here in the left panel, we show the track of Hurricane Gonzalo, and starting from tropical cyclone at October 13, and start to intensify pretty quickly until it get to Category 3 and Category 4 hurricanes around the curvature. And we also see the blue, well, it's a little bit black here. This is the trajectory of the two underwater glider in the 2014 hurricane season from the PhD. So we can see it kind of do one in the Caribbean Sea, one in the North Atlantic Ocean, collecting some very good data. And in the right panel, we have the intensity of Hurricane Gonzalo. You can see it starting from October 13, 0Z, and underwent rapid intensification. So increase 35 knots wind in 24 hours, then continue to intensify and reach to 125 knots in maximum wind and 940 millibars in the mean sail pressure when it's at its peak. And we can also see there's a temporary weakening around the wind and the mean sail pressure on October 16, which is indicating there's IWO rhythm cycle, which is not the focus of this study. Okay, so here I'm going to show some of example of the ocean observation other than the glider water, other than the underwater glider we simulated here. So that's what we call the standard ocean observation. That's from different ocean observation platforms. This is an example of the 2 weeks before we starting the couple forecast for Hurricane Gonzalo. So you can see we have the satellite altimeter sea surface height. We have XBT, Argo flows, drifter SST, boil SST, and shipbound SST. We can see during this 2-week period, we don't really have any XBT profile available. And among all the observation platform, the shipbound SST and altimeter sea surface height has a larger coverage compared to the others. And the data simulation system we have used here is a so-called statistical interpolation data simulation system. And in this data simulation system, you can it's flexible to specify the background error covariance. So we have different options. In this case study, we used the stationary ensemble to represent forecast error covariance. So which makes this one is so-called ensemble optimal interpolation. We have put some reference here. It's already used by the others before.
Jili?
Yes.
Quick question. How many of these ops are getting into RTOPS?
I think RTOPS should. Okay, so the RTOPS starting with the encoder from the NRL. Seems to me they should use all of them.
Okay.
Yes.
All these standard ocean
The
observations.
reason I ask is that this year we're starting H4 from RTOPS, so I just wanted to get.
Right, but in EMC, I think RTOPS they also do a spin up, so they call it nowcasting and forecast.
Right,
So
for POM they do the spin up, but they're starting with RTOPS.
right, yes, they use all of these standard ocean observations. So the model here we use is H-Wolf HiCom coupling system. For H-Wolf model, it's 3 nesting domains with 27 to 9 to 3 kilometer with a finest of 3 in the innermost domain. We have 61 vertical levels. Physics use H215 physics. We do use a vortex relocation and initialization for H-Wolf, but we don't really simulating any atmospheric observations here. For HiCom model, we have 1/12-degree resolution, 26 vertical levels, and the mixing scheme used here is a K-profile mixing scheme, KPP. And for coupling time is around 540 seconds, so it's 9 minutes coupling time. So here is 4 experiments we are going to do. We perform here in this study to investigate the data impact. So the first one is our baseline, is the so-called no data simulation experiment. So we start the forecast from 2009. I didn't show it here. So all of here showing is in 2014, but we started from 2009 from the GDAM climatology. Then we run a very long time free forecast of HiCom until October 13 at 2014. Then we started the coupled forecast for Gonzalo. The second one is we call the glider experiment. This one is the same as no data simulation, except starting from July 15 of 2014, we perform the daily glider ocean observation simulation with HiCom. And start at the same time, October 13, we run the coupled forecast. And the third one called the control experiment. This one basically the one we only simulating the standard ocean observation. So we're starting from the March 1st when we start to run the daily standard ocean observation simulation with HiCom. Start at the same time, run the coupled forecast. So the last one, we combine these two together, basically you can see. It's starting to run the daily standard ocean observation simulation starting from March 1st. Then from July 15, we add the daily glider ocean observation simulation. So this one, basically we combine all the available ocean observations and start at the same time, run the coupled forecast for Gonzalo. Okay, so let's first take a look at the subsurface profile, because pre-storm ocean subsurface structure, the thermal and saline structure, is very important to the ocean response to hurricane and the ST cooling. So here we have the 4 profiles extracted from the model compared with the glider observation at October 13th initial time. Here in this small map, we have the red dot here show the location of the glider at this time, October 13, 0Z. And the green dot, here we have the location of Gonzalo there. So the left one is temperature profile, the right one is salinity profile. You can see from the temperature profile, its observation give you around like 55 meter isotherm layer or the mixed layer with SST of around 29 degree. And if you don't have any ocean observation simulated, the no data simulation, the blue one, we see basically underestimate both the temperature and salinity with a shallower mixed layer. And when you're simulating the standard ocean observation, the right one, you can see it the structure, both temperature and salinity structure, is improved closer to the observation. And when you're simulating the glider observations, you can see the purple one and the green one, they generally give a better representation of the temperature and salinity structures. But the best one seems from the purple one, best fitting the observations. That's the one we're simulating both glider and the standard ocean observations. Okay, so to see it more clearly, we have a difference between the model and the observation of the profile. The upper is the temperature, the lower is salinity. The y-axis the depth, the x-axis as a difference. So because there's a difference, and the zero line, left of the zero line means underestimate the temperature of salinity. The right one means overestimate. So as we see before, if you don't have any ocean data simulation in ODA, in general, both temperature and salinity, there's an underestimation. The bias is always negative, and you see around the 55 meters or below the 100 meters, the difference is always over 1 degree. And when you're simulating the ocean observation, the error is reduced. All of these three experiments, the error is smaller. And the best one is from the purple one, with a small error compared to other experiments. And throughout the whole 150-meter depth, and also around the surface, which is very important to the air-sea interaction.
Jili, is
Yes.
this the O minus A, the analysis?
Right,
or
that's
the
this
actual-
model minus observation.
But it's at the analysis time.
Right, yes, that's analysis time. That's not
It's actually A minus O.
A minus O, but yeah, it's
right. Yeah, it's analysis minus observation. Yes.
Noda, he has no data. Glider is assimilating only glider
right, but it's
data.
what I'm
Control.
saying is at the analysis time, not at any forecast time.
Yes.
yes.
I think it's right.
Because as
That's
the forecast runs, you're doing the coupling and you're seeing the interaction.
Yeah.
right. So this
This
is just
is the
the initial
analysis.
condition after analysis. That's correct. Yes. So for the salinity, we can see there's a very small error throughout the whole 150 meters. Most of the time, it's very close to zero.
Any idea what's going on at 55 meters with the
They don't get
temperature?
the mixed layers.
We didn't really show below 150 meters.
No, 55 meters with the
55 meters.
What's that?
Right, that's
Sudden-
basically around the mixed layer depth. So apparently,
Oh, okay. So
you see
where
here
have
it's
the
not
lowest
really
data.
doing a very good job. So that's the part we need to improve.
KPP.
Yeah, that's a lot of the corrections due to altimetry, and you have to estimate the correction profile for temperature and salinity from the
Well,
anomalous test, and it's not doing a good job with the mixed layer structure.
well, how does your interpolation for your, how do you weight the vertical structure when you do the assimilation? Your assimilation system has got some weight in the vertical, so you're
Right.
probably smoothing out those levels.
Well, when you simulate altimetry, we're using the so-called Cooper-Haines method, which primarily corrects the area around the main thermocline. It doesn't really get the structure correction right for the mixed layer. So that's an area where we can potentially improve by looking at synthetic profiles
Yes.
that would resolve that structure. I think there's room for research there.
Yeah. So then we also calculate the tropical cyclone heat potential or ocean heat content, which is defined as a temperature integrated from a 26-degree isotherm to the surface. So we show you here the number in the red. Observation has a relatively large value of 86 kilojoule per centimeter, and nodal simulation have underestimated the TCHP with a value of only 59. And other data simulation experiments, ocean data simulation experiments, have a value much better than the nodal simulation, closer to the observation. Another interesting feature we see here is we have a 55-meter isotherm layer, but we also see a sharp increase of salinity from surface to around 20 meters. So this sharp increase or the stratification of salinity will lead to a change of gradient of density. So that will create a so-called barrier layer. So the reason we call it barrier layer because this barrier layer acting like a barrier to resist vertical mixing. So it can reduce acid cooling. So to investigate that, we have here the plots of density profile and the buoyancy frequency profile. We only plot the upper 70 meters for this case. We can see there's a change of gradient of density around 20 meters, and from the observation, the black one, and the two experiments simulating underwater glider observations, the purple one not very clearly. The purple one, the green one, has a better density structure retrieved compared to the other two experiments. And it's more clear in the buoyancy frequency plot here. You see there's a local maximum around 20 meters, which shows a strong stability around this level. And there's the only two experiments that have this correctly retrieved is the two simulating the underwater glider observations. So that basically tells us it's one of the interesting results we have here is only by simulating the underwater glider observations we can correctly retrieve the structure of the density, the buoyancy frequency, the stability, and the barrier layer in the model, which is showing the importance of the underwater glider observation simulation.
How does that, how do they get that from the altimetry? Do you retrieve salinity? You can't get
You
salinity.
just to use in historical relationships between
Yeah.
sea height.
So I think
and
it's
the
yes, it will be very hard to get.
Chronological-
Yeah, so
Yes.
you may or may not get it from altimetry. Yeah.
Right.
Okay, so next let's move to a larger area. We're going to take a look at the data impact on the SST field. So these 4 panels on the right, we have the SST from 4 different data simulation experiments or no data simulation experiments. On the left one, the corner one, we have the observation from remote sensing microwave infrared satellite SST product. So the most important feature we see here is Atlantic whirlpool, which is defined as 28.5 degree, the SST over 28.5 degrees, the warm water here, highlighted by the solid line here. We see the whirlpool is kind of dominated the Caribbean Sea and part of the North Atlantic Ocean. And this feature is basically kind of missing the nodal simulation experiments. We see there's only small patches of area with SST over 28.5 degree, and it's hardly reached to 29 degree here in nodal simulation experiments. And when we are simulating the glider observations alone, we see there's an improvement and reduced SST error around in the regions surrounding the glider observation locations. When we are simulating the standard ocean observation in these 2 experiments, either alone or with the glider observations together, we see Atlantic whirlpool is much better retrieved in the coverage. So to more quantitatively evaluate the data impact on SST here, we averaged SST within the 2 radius max wind from storm center, and we plotted along the projected storm tracks. So the y-axis is the value of SST, the x-axis shows actually the track locations, projected track locations of the storm. We put the track hours here. So from 0 to 120, that's corresponded to from the southern end to the northern end of the track. So we can see here the black line is observation. You can see from 18 hours to 96 hours or to 90 hours, most of the time the average SST is around 29 degree. And without any ocean data simulation simulated, the blue line is never reached to 29 degree. And when you're simulating the glider observations along the green one, you can see it's the SST error is largely corrected around the location of the glider observations. And when you're simulating the standard observation, which is the red one, you see there's a large improvement basically from the 18 hours to the 90 hours. It's follow the observations quite well here. There's over 1 degree improvement in the later part or in the north part of the track. And when you're simulating everything together, that's the purple one, it seems like you have the best results. It's also reduced the difference, SST difference around the glider locations.
Is this the same track in every case?
Right, yes.
Okay.
So here we have the data impact on the TCHP at the initial time. We have the 4 experiments here on the right. The left is a observation from the PHOD TCHP product here. We see the similar story here. The nodal simulation basically along the storm track, the TCHP is kind of small. And when you're simulating the glider observations along, improve the TCHP around the location of the glider. And when you're simulating the standard observation, these 2 experiments have larger TCHP along the predicted storm track. Right, so the next several slides, we're going to show the data impact on the forecast. So the first one we have here is First, we're going to look at the ocean, the direct impact on the ocean forecast. So here we have the difference between the model and the observation. The observation is a glider at the same location we've seen before in the profile plots here. So we plot these difference contour with depth and time. So the vertical, so the y-axis are the depths, the x-axis are the forecast time. So we only show the first 48 hours, starting from October 13 to October 15. Without any ocean data simulated, we can see, okay, because this is a difference, so the blue one, the blue color means the model under predict the temperature, and the red color means the model over predict the temperature. So we see in the no data simulation experiments, it's everywhere basically it's a blue. So that means the model is under predict the temperature, and most of the time it's or below 30 meters depth, it's over the difference is over 1 degree, around or over 1 degree. And when you are simulating the standard ocean observations along, you see part of the error is reduced above the 30-meter depths, but below 60-meter depths, you see everywhere is turning red. So that means these experiments over predict the temperature below the 60 meters. And when you're simulating glider observations along, you see the error is also reduced in the above and below. But there's still a negative and positive bias mixing together around the mixed layer depths. And seems that the best results in generally is from the one you're simulating the all available ocean observations. It generally have the smaller error compared to the other experiments. So this one is salinity. So the same difference. We have a similar story here in the no data simulation. It's all blue. These experiments also under predict the salinity during most of these 48 hours forecast. When you're simulating the glider observations or standard ocean observations along, you see below 60 meters the error is reduced, but above that is there's still a negative bias there. And here we can see very clearly that when you're simulating all the available ocean observations, the error is reduced further, much further. And during most of the time, the difference between the model and observation is smaller than 0.3. Right, so here we see the data impact on the track intensity forecast for Gonzalo. Left panel we have the track here. So apparently in this particular case, it seems like the track is not that sensitive to the ocean data simulation. All the track forecasts are stuck together. Because we're using the same initial condition, same initial atmospheric condition, so it seems like in the 5 days forecast, the different ocean initial condition did not make a large impact to the large-scale atmospheric environment.
Looks like there's a slight speed error in one of them.
Right, about the speed, I don't plot the translation speed here.
I mean, the track is fine, the direction, but the speed.
Right, before the recurvature, it seems okay, but after the recurvature, especially in the last 2 days, it seems like the best track shows the speed up, but not in the model.
The models are too slow.
Right, that's slowed down. So on the right side of the we have the upper panel is a mean sea level pressure. The lower panel is maximum wind here. We see compared to the best track, which is the black line, if you don't simulating any ocean observation, the blue line here, you see there's definitely an under predict of the intensity of around 18 millibar and 35 knots under prediction when the storm is at its peak. And when you it seems like simulating underwater glider observations along, the green one did not improve a lot. And when we simulating the standard ocean observation, the red one, we see definitely improved intensity forecast, especially after 36 hours. It's pretty close to the best track in terms of mean sea level pressure. But for wind, even though there's still some improvement, it's getting stronger, but we still under predict the wind. That's one of the problems we have, the over prediction of the storm size. So it's storm is too large. So if you have a same center pressure, the pressure gradient will be small. So we will have a weaker wind here.
Jili,
Yes.
how many forecasts is this? Is this one forecast?
Yes, this is just one cycle. Yes. We're going to do more cycles in the future. That's for sure. Yes. Yes. So.
Because there may be a residual impact.
Yes.
I mean,
Yeah.
you're starting on with July 13th, the obs, so.
Right, yeah. So then based on this one, on the right one, after we simulating the standard observation, if you also add the glider observation, we see some improvement around 96 hours from the wind by simulating all the available ocean observations. So
That suggests there may be an impact. That's 4 days after the storm.
yes, exactly, yes. So to confirm that, we calculate the so-called integrated kinetic energy within the two radius maximum wind on the left panel. Even though we don't have an observation to compare with here, but we do see there's larger energy here around 96 hours corresponding to the strong wind before compared to the other observations. The purple one is the one we're simulating other available ocean observations. So we do have a stronger storm around this period. And this also consistent with here the total surface density flux with forecast time. We see there's a local peak, local maximum here for the purple one compared to other experiments. So we do have a larger surface flux other than the other experiments.
So the storms are bigger, or maybe the 34 knots are better, radius of 34, or 50 knots is much closer to what is observed?
Right.
How
yes,
is the
yes.
IKE getting so good, even though the peak wind isn't? It's-
Well, he doesn't. It's
gotta
not
be
necessarily
structured.
getting good because
Right, because there's no
no
observation here, but
Right.
we only show you the storm.
I can get you the best track IKE. There's a way to calculate it.
Okay.
Yeah, you can
Okay.
calculate those. But, I mean, the idea would be is the structure better.
Right. Yeah. Hopefully, yes.
Yeah.
Okay, so that's all the results we present here today. So in this summary, the simulation of underwater glider data improves the pre-storm ocean thermal and sealing structures. And the barrier layer is only retrieved with underwater glider observations simulated. There's one of the papers from Ricardo et al. Have a very good detailed analysis of the observation barrier layer structure. If you're interested, you can refer to this one. And the ocean data simulation significantly improves the Gonzalo's intensity forecast. And when added to the standard ocean observations, underwater glider observations shows a larger impact than assimilated alone for the intensity forecast. So this is work still ongoing here. We are also, right now, is also investigating the potential impact from assimilating data from more underwater gliders with the ASI framework. We already designed a network with more gliders to cover more area to see if more glider observations will have a larger improvement. And definitely there's more cycles and cases need to be tested and evaluated to obtain so-called robust conclusions. Right now we're also doing their denial experiments to examine the different ocean observation platforms impact. For example, we separate the altimeter sea surface height with other observations, and we want to see which one have a larger impact among these platforms. All these results we're trying to summarize and document in one of the manuscript we are preparing right now. And thanks, that's it. Okay, so any questions? Yes.
I'm very interested in the barrier layer impact. Can you isolate that versus the SST impact on the forecast? I mean,
No.
Ricardo, are these barrier layers
Yeah.
just in the area that
Yeah.
you're sampling, or are they prevalent everywhere?
So can you go back
Sure.
two slides?
And
Did
to the
you go? No, I think you went back too far.
this one.
Go forward. No,
The
forward.
other way, the other way.
Okay.
Forward. Onto the salinity plots. There you have the sections.
This one.
No, the sections.
Towards the end.
The forecast.
There.
Back. One.
There.
This one. Okay.
So you see the salinity differences on the top. The red salinity biases, that the positive salinity differences. That's the region that the barrier layer is confined to. It's very restricted area, confined to it's very local, but we do believe that that could potentially had an impact on the storm.
Do
So-
we have other means of getting independent, like AXPTs or
Argo.
XCTs, XCT, Argo?
Yeah.
So Argo would be able to validate, because one of the things is, you know, barrier layers have always been talked about as a problem in the Indian Ocean in particular, because of, you know, the monsoon rain and it changes the whole salinity structure. It's very impactful there, but I'm wondering, you know, about in our coastal water.
Well, there are a few things with this barrier layer that we still have to study. Okay, we identify the model didn't get the barrier layer. We got it with glider, so why didn't have a bigger impact in the intensity forecast? So maybe it doesn't have the same impact as the Indian Ocean. And then glider helps you get a very good ocean. So why that doesn't translate in a better intensity forecast?
Yeah, well, it seemed like that all OBS, and if you go back to the differences, the all OBS and the glider are subtle, the differences. Are very
When you
subtle.
have, well, it shows is when you have glider alone,
There's only a
you
local,
you improve the ocean, but you
Only
don't
locally.
the intensity.
right,
But if you have the glider on top of other observations, improves the intensity forecast greatly, and that if you didn't have glider.
yeah, that's
So
why.
you need the other observations besides glider.
Right, and if you go back to the one where you were showing the differences of the horizontal, one more, two more, the SST. If you look at the bottom two, they look very similar, at least here, but in TCHP, they look a little bit different, so.
They both are too intense.
Right, but if you look at just
Only
glider
part, yes.
alone, it only impacts the area where the gliders are.
Oh yes,
Very
yeah.
closely because of the
Right.
way he does the DA.
Mm-hmm.
If you remember from our idealized study,
Right,
when we changed
So-
ocean conditions,
yeah,
it took the model storm 12 to 18 hours to substantially react to that.
Yes.
So if you're only correcting a small area of the ocean, that may not
takes a
have
long,
time.
right.
Now, that means that gliders are important, but maybe multiple
Right.
gliders covering a larger
That's
area
right.
will be the strategy to follow in the future.
Or the combination of
Of-
Argo and the glider.
and
Well,
Alamo
that's
floats.
why a glider alone will not give you the improvement that you want, but if you add glider to the other observing systems, there when you see the large improvement,
Right,
because it helps you to identify all these little features that are important.
Can you do
That is
OSIs?
for the ocean.
Sorry, can you do OSIs where you add multiple gliders?
Yes,
we're doing-
right now we're
we're
doing
doing
this
that
right now.
now.
Yes.
It's been done.
We haven't put it into a forecast yet, but we see, larger improvements over a larger area when we put multiple gliders in,
Yes.
so hopefully it'll have an impact.
Julie, very
Yes.
interesting talk. Do you think you could test your theory about the barrier layers by, instead of using climatology that doesn't use glider information, swapping out, what you've learned from glider observations and replace your salinity synthetic relationships with glider synthetic relationships?
Yes, I think that's a good suggestion. We have some discussion before, I think with Sanki and others, about how to design experiment to hold Frank's question about how to isolate the barrier layers impact from the SST, because right now if you have the different SST, you also have different TCHP, you have different barrier layer, the structure, there's too many factors involved. So we're trying to find some way to do that experiment. Yeah, so it's still ongoing work. Yes.
Jili, does your result suggest that the SST still have the most impact, right? I mean, so SST have more impact than the mixed layer depth and also salinity.
I don't know if we can say that because as I said before, there's too many factors involved. So it's not just when we talk about the ocean, it's not just the SST there, because if you use a coupled model, it's not different. You can see the differences in SST. But everything is different, so it's really hard to say right now. It's only the difference from ST or difference from the TCHP or from the barrier layer for mixed layer depth. So
We have to analyze a lot more storms, a lot
Right,
more
we have
forecast
a-
cycles to get
yes,
good
to more
statistical
cases
picture.
and more cycles to really
When you want
identify.
slow moving storms, you want large storms, you want, all
Right,
kinds
the
of
storm
parameters
transient speed
based
is
on
also a
that
factor.
value.
The altimeter denial experiment would also show that, like, where you're giving it SST, but you're denying the altimeter for the depth of the.
At this experiment, we only deny glider.
Right,
That was
understood. Understood
to
the
study,
event.
and then now he has everything to start denying the other platforms. And with respect to SST, the upper ocean drives the SST. So to get that SST, even if the SST is the only one, you still need the upper ocean, which is driving the SST.
Right,
Right.
but it would be real interesting to do like Edward or some of the other cases that didn't actually go through the glider array to see how much the glider array impacts the aerial forecast. the other data, obviously.
Okay.
Because, you know, it may be, as George was saying, you know, the area, if you can improve the aerial coverage, like the whirlpool stuff
Right.
that he was showing, that would make more of an impact of the gliders globally or over a bigger area
Right. Yes.
by anchoring that,
Yep.
that vertical structure better.
Yes.
But another comment is, maybe in the future you're planning to do that, it'd be nice to show how all these parameters or data simulation affect the structure of the storm.
Yeah,
the hurricane.
structure.
Right,
The
yes.
asymmetry of the cooling, SST cooling, have you look at that?
We just take a quick look about the hot ruler of the, say, the 900 millibar wind structure. The one with all the data simulation, with all the ocean data simulated, apparently have the stronger storm. But right now, we didn't really compare with observation. So the next step, I think we're gonna do the structures. Yes.
Well, and to really test the model, you wanna look at how the forecast fields look to the ops.
Right. Yes.
As the model, so, you know, that 13-0 run that you're running, I mean, it starts when the storm's back. You wanna see
Right.
how the forecast looks at the ops time.
Right. Yes.
See how well the model did in representing forward in time.
Right.
Cause it's like 2 days before it hits the buoy, the glider.
Right.
Storm.
Yes.
That would be really interesting.
You
That'd
just-
say how good the model
Are there plans to get that data in operationally to the data stream?
It is
The
now.
glider
It
data?
is.
It is now.
Glider should be in the.
It is?
It is now.
So it should be assimilated into operational?
Yeah.
Yeah.
Yes.
It goes into the GTS.
The RTOS
So
has to use it, that's what we have to
They use
find out.
everything that is in the GTS.
But they weren't obviously during that time period.
Oh yes.
Yeah.
We always transmit it in real time.
Yeah, they were.
So they should. Yeah. They should doing this in the.
Is it getting into RTOS, that's the question.
That one I don't know.
I mean, it's a forecast that we ran in that time, RTOS was not the initialization, only this year.
Yeah, so it is getting into the Navy project.
Right, so if it's getting to Navy, then should see it this year, because we're using RTOS to initialize this year for the first time, even though
Okay.
they're doing some hocus pocus.
Yes. Yeah.
And it is Palm, not Hycon, but in the parallel runs, it should be there.
Okay.
You'll find out.
Yes.
Gustavo, we're having 4 gliders here?
Yes.
2 north and 2 south?
Huh?
2 north and 2 south?
Should thanks. So should
One on
turn this
the
off? Yeah.
One on the bottom, well, one on the bottom.